Welcome to Section 5, TensorFlow in Production. One of the main reasons to choose TensorFlow over other frameworks is that it was designed for large-scale distributed training and inference. This section shows how the advantages of TensorFlow are utilized in production environments. The section begins with an overview of the production setting and requirements for models in such a setting, as well as a sneak peek at some distributed TensorFlow stuff. Next video will provide a primer on the TensorFlow C++ API, which will be necessary to understand the code in the subsequent video on TensorFlow serving, which is a high-performance serving system for machine learning models designed for production environments. And lastly, we'll look at the brand new TensorFlow Lite, a lightweight solution for model and embedded devices. This will allow us to deploy our models in the context of mobile applications. Feel free to skip around this section since the videos don't need to be watched in any particular order, with one exception. It's a good idea to watch the C++ video before the TensorFlow serving video. Also note that it's strongly recommended to have familiarity with C++ before watching those two videos, otherwise they'll be a little difficult to follow. And finally, if you don't require high-speed C++ environments, learning a little bit about TensorFlow C++ API can still help you understand the inner workings of TensorFlow one step deeper. Remember, all your models are ultimately sent through a TensorFlow session, which essentially just passes everything to and from the underlying C++ runtime. Today, we'll be getting a general idea of what's required for our models to function at scale in a production environment. The processes involved in implementing models in a research setting versus a production setting are vastly different. So it's important that we understand the need for a full section on TensorFlow in production. We'll begin by introducing a handful of key concepts to keep in mind when writing models in a production environment. Then we'll look at a few of the most popular options for serving and deploying our models. Lastly, we'll do a small primer on ideas in distributed TensorFlow. This is the process of distributing our TensorFlow computation graph across multiple devices and possibly multiple machines. So there are a few key requirements that any production ML system must have. For one, we of course need our models to be as fast as possible, specifically when making predictions. No one is going to want to use your model if they have to wait a long time to hear back from it. I've listed a basic requirement that any single prediction should be less than 10 milliseconds, but even that is too long for high-performance applications. Ideally, you'd want to be shooting for sub-millisecond prediction times, which is certainly no simple feat. Next, your model needs to be battle-tested. Do you occasionally send a request to your model and it crashes for some strange reason? Things like that are considered catastrophic failures for a model in production. This means you should be very aware of the kinds of inputs your model can handle, and if there are any cases that could theoretically cause problems. Those must be addressed somewhere in the code, depending on whether you think it's the server's responsibility or the model's responsibility to handle such problematic inputs. Another crucial component is reproducibility. For example, let's say I come to you and ask for an exact replica of the model that you deployed on a specific date, and I also wanted the exact set of data that it was trained on, along with the associated metrics plots and anything you measured for its performance. Could you provide that for me easily? This is the kind of attention to detail that is mandatory in production environments, would be rather unnecessary in a less formal research or development environment, perhaps overkill. Lastly, we need to be much more resource aware than we'd need to be otherwise, since running our models on our servers is not free and it can become expensive as we get more and more using our application. This means taking the time to fix a bottleneck in your computation graph that's hogging more resources than it needs to be can really pay off, literally. So one of the first things we need to do to put a model in production is we need to choose a server and a deployment service. To be clear, there are tons of choices out there, and I've only listed a few of the most popular options here. To get straight to the point, if you have the flexibility to choose whatever you want, I'd suggest Google Cloud's ML engine. This handles both serving and deployment for you for your TensorFlow models, and that's pretty incredible. They also have many guides, tutorials, and overall excellent documentation, and it shouldn't be much of a surprise that serving and deploying TensorFlow, made by Google, is easiest with Google Cloud. So you might be wondering why even list the other options. Well, it's quite common to be in a situation where you're already set up and integrated with another service, such as AWS for example. At 4JI, where I work, that was the case, and it made little sense to move over to Google Cloud just because it makes deploying TensorFlow models a little bit easier. And furthermore, it's always true that binding yourself to any particular service comes with at least some decreased ability to customize. At Forge, we experimented with both TensorFlow serving and various custom server implementations in C++, and we ultimately ended up choosing a custom implementation since TensorFlow serving only worked with HTTP 2.0 and gRPC, which did not really integrate well with our existing architecture. So as you can see, there are a lot of considerations needed before jumping into deploying your models. Okay. A must-know feature of TensorFlow for production work is its support for easily distributing work across multiple devices. This is going to be just a quick primer to ensure you're aware of the functionality, and the detailed overview of distributed TensorFlow is linked in the additional resource slide. In the simplest case, where we are just training on some local machine, such as our computer, and we want to specify how our graph is going to be distributed over our available devices, we use the tf.device function in a with statement, as shown here. In this simple example, I've created two variables, x and y, and specified that I want them placed on our CPU. Specifically, I'm saying that I want x and y's associated operations on the CPU. Remember, variables in TensorFlow, each variable has an associated operation. And next, I've defined z to be the addition, x and y. It's common practice to place math operations on the GPU and variable operations on the CPU. And lastly, instead of launching the default session, I create a server. This is what's used in distributed training environments, TensorFlow server objects. I've used the simple create local server static method to instantiate one of the simplest kinds of TensorFlow servers, and I've shown an equivalent way of creating such a server explicitly in the comment right above it. So they do the same thing. This returns a TensorFlow server object, which is associated with a unique task in TensorFlow terminology. For the simple example here, the words task, cluster, and server are basically the same. We'll see the distinction in the next example coming up. To run our addition operation using our server object, we instantiate a new session, tf.session, and we pass server.target as its first argument, which is target. The value of server.target is just a string, gives the URL for connecting to our server. In the case of this example, server.target would be localhost with the gRPC protocol, and we're going to learn a lot more about gRPC in the video on TensorFlow serving. But let's now see an example that's one more step involved in this one. First, notice that I'm still building the same graph as before, containing x, y, and z. But now, however, notice that all three of these are under the same tf.device block. And instead of passing a string to tf.device, I've passed a function. The function is expected to accept a single argument, which represents an operation node in our graph, and TensorFlow will call it on all operations we create within our with block. The result is the same as before. Variable ops are placed on CPU and math ops on GPU. But doing it this way allows us to customize device placement easier for more complex graphs than seen in this simple example. I've also wrote out the long device name explicitly instead of the simpler /GPU/CPU we saw earlier. In this case, they end up getting mapped at the same device, but it's useful to see it written in this way so that when you move on to more advanced use cases, you aren't surprised when you see the long names, since then you'll need to use them if you really want to distribute work across multiple servers. This is how they look, however, when we're just distributing work across two devices on the same server, and when that server is our local machine. Also, remember when I said earlier that task and server basically mean the same thing for us in this example? Now we can see a little bit why. In the long name, you can see that a portion of it says task:0. Everything in our example is task 0, but you might have situations where you want more than one task, as would be common for machines that have many devices on them, and models that have many operations that can be parallelized, so we can use multiple devices in parallel, but that are computing things that we want to keep distinct, and so we can denote them as having separate tasks. It's more of an organizational thing that's available to us should we want it. Also, in addition to the good practice of placing variable ops on CPU and math ops on GPU, another good practice is to place preprocessing, aka your input pipeline or your input function, on the CPU as well. This is automatically done by TensorFlow estimators. Their default behavior is to place everything inside your input function on the CPU in order to free up the GPU's resources to focus on training. Anyway, that's all the time we have today for distributed TensorFlow, but make sure to check out the additional resources slide to hear more about it. As always, make sure to read through the links here for an in-depth look at the topics covered today.